This conference will now be recorded.
So welcome everyone to another OCP TAP session. This is call number 82. We have Julian St. James from Meta today giving us a talk about precision frequency measurement, or PFM, which is like a complement to PTM, where PTM basically does synchronization with phase. This will be a synchronization for the frequency. So as usual with the format, we introduced our speaker. So as I said, Julian St. James is a network hardware engineer at Meta. Prior to Meta, Julian worked at A10 and Cisco as a hardware designer, which he worked on network hardware appliances. Julian has been very active on OCP TAP project, supporting multiple work streams and all the evolution of the time card with the newest features. Julian's latest work has been on precision frequency measurement, PFM, to add to PTM to bring precision, time, and frequency sync to the heart of the systems. And again, I can't be more thankful to Julian for all the work he's been doing on the time card. Like you can follow on timingcard.com or timecard.ch with all the revisions that he is always putting on, and like so many more things like time card mini and the latest one, which is like a White Rabbit enabled NIC, which the hardware is already up, but I mean, we're still in progress of testing things. So Julian, with no further ado, the floor is yours.
Okay, great. Thanks for the intro, Ahmad. So like Ahmad mentioned, today I'll be talking about PFM, similar complement to PTM, which Kevin presented about, I believe, 2 weeks ago. And so just as a start to the presentation, this might not be surprising to a lot of you, but just as an intro to the whole idea, what is a clock? So when we talk about a clock, we're talking about a periodic system, so the period being the frequency that measures time. So your time is the exact number that you think the time is based on that clock at a specific instance. So the two examples that I have for this, a lot of my examples I'll try to relate back to cars, kind of easier to understand. Basically, your frequency is your speedometer, so that's how fast you're going. And then your time is your odometer, so basically how far have you gone. So this is frequency versus time. And another way to look at it is basically where do you typically see frequency versus time? So for example, the clock in your car is a time. You're not usually adjusting the frequency of your car clock. So you might look at your car clock and it says noon, but you're not going to see another dial in your car that says, okay, change the clock frequency of your car clock. You're only going to be able to adjust the time. And then the other side of it for frequency is something like music, where usually for a composition for a particular piece, you would say, this is the beats per minute of this piece for this section of the music. And you're looking only at frequency in that case, not time. So you're not looking at, say, this is note 10 versus 11. You're saying, okay, just play these notes at this frequency. So these are the examples that I have for clocks. So in the case of frequency, most of this is about frequency, like I said. So I was looking at different ways that you can transfer frequency. One way transfer is where you just send the frequency directly. So the example for this that's at the top of that diagram on the right is you have, like, let's say a metronome that's playing an audible frequency that everyone in the orchestra is listening to. So all of your players in your orchestra are aligned to the same frequency now, because they're getting just directly from the source. The second part is more integral to what I'm trying to present today, and I'll go into that in another slide in a second, but the idea is basically, okay, instead of having your source give a frequency directly to your destination, you have your source and your destination listen to some other source, and then they can talk to each other over a data channel and compare what they see versus that reference. So they can't directly measure from the source to the destination the frequency, but they can both see a common frequency. And so I'll get a little bit more into that in a second. Just to expound a little bit on the one-way transfer, basically you get exactly the frequency from your source, and you know that that source frequency is a particular value. So for example, with a PLL or a DPLL based system, you tell it, okay, from this input source, you're getting a 10 megahertz reference. And the destination will just follow that, thinking that's a 10 megahertz source, and generate whatever other clocks it needs from that source. So you either multiply or divide, but you always consider that source to be your source of truth for frequency. So it's exactly 10 megahertz. And so in terms of hardware designs, this has some downsides in that your source has to directly connect to every destination. And that means that you have a lot of connections. So if you have even if you had a cesium clock with 10 ports, you can still only support, let's say, 10 destinations, and then you have to cable all of that. So it's not very scalable, and you need a lot of connections, and you also can't do any kind of other sources. You're just getting from one source. So the other way that I'm more presenting about today related to is the common view transfer. So this is this diagram is from an NICT publication comparing different ways to transfer frequency. So the way that this mechanism works is your source. So let's say you had an atomic clock as your source, and your other device, your follower device, where you want to get that source frequency onto it, they both watch some other device that is giving them both frequency. So kind of a rough example for this is a GPS system where you're watching multiple frequency sources and comparing them. Not a great example, I know, but it's kind of a similar idea where you have a device that has a common view of multiple sources. And for a kind of a general idea of how this operation works, the example I list here is, let's say you have your source, which is your golden truth frequency device, and your follower or user device, and they both can measure versus themselves versus some reference that they both see. So in the example operation, your source device would measure versus the reference and say, for example, it measures it's 5.5 times faster than the reference. The user or the follower will measure versus the same reference and see that it measures 5.3 times faster. And then your follower or user device will ask the source, what did it measure for that measurement? So they would see like, hey, the source measured it was 5.5 times as fast, and you measured, okay, you're 5.3 times as fast. You need to speed up a little bit to match the source. And then you would keep that loop going, basically measuring versus the same source and trying to match the measurement at both sides. And so the upside for this is that you only really need a data channel between your two devices. If you have a source clock and a destination clock, the only communication they have between each other is a data channel. It's no longer a frequency channel. And the only thing that you need to worry about basically is that you have some common clock that they can both measure against. And you need to be able to measure, obviously. But you need to have the data channel and then a common clock to make this architecture work. And so my goal for kind of this presentation and this architecture is trying to show a way to build a frequency lock system with as little custom hardware or custom equipment as possible, and to make that easy to scale up and add more capacity, or scale out and add more units, and to make it easy to build using stuff that already exists. And so the TLDR of that is to use the 100 megahertz PCIe clock as the common view reference clock. I'll get more into the details, but that's the gist of it. So to go a bit into the hardware details of what I'm proposing the architecture look like, today there are chips called DPLLs, which are digital phase lock loops, and all of the clocking implementation is in a digital domain now. So typical PLLs will have a voltage controlled oscillator, and they'll measure the error signal as a voltage and feed that back, but that's all in the analog domain. And so nowadays there are DPLLs where they have multiple inputs and multiple outputs, and they can generate multiple outputs from a known input frequency, same as a PLL, but they're doing it all with digital values. So this is all in the digital domain here, where you have, the diagram might be a little small, but your phase detector and your calculations in terms of loop filter and dividers are all digital values that you can program and change and read back. And so some of the key features in addition to that I'm looking for in DPLLs is two things. One is called hitless switchover. So this is a feature where if you have, let's say, two inputs, and let's say you're listening to two atomic clocks as an example, if one of them dies, the one that you were primarily tracking, you can switch over to the second one without glitching. So the DPLL will keep track of the relationship between one input and another, And if you lose one input, it will switch over to the second one without you seeing a degradation on the output. The other feature that I'm mainly taking advantage of is what's called a digitally controlled oscillator. And so you might think that this is you're writing a frequency value, but actually what I'm doing with this feature is I'm writing the error value. So like in the previous example about you have a source and a destination, make a measurement and record that error. Basically, I'm using this feature to take that error value and put it into my DPLL and tell it, from that example, it was like 5.5 versus 5.3. You would take that 0.2 difference and feed it into your DCO, and then that would generate the frequency you're trying to generate. You're not telling it generate 100 megahertz. You're telling it, okay, you're a little bit too fast from where I want you, or you're a little bit too slow, and you would use that instead. So this feature of a DCO is what I'm leveraging. And so to talk about the system architecture that I'm looking at, I'm mainly interested in server architecture, so commercial off-the-shelf servers. And when you look at what a server has, they have CPUs, obviously, and they have peripheral devices. This is your like USB and hard drives and stuff. And they have PCIe slots. And so typically you would use your PCIe slots to add functionality to your server. And so when I look at what a PCIe card gets me, what do you have connected from the motherboard to a PCIe card? One of the connections is 100 megahertz reference clock. So this is mandatory from PCIe. So every slot in your motherboard, server, home computer, everything, they all get 100 megahertz reference clock from the CPU. And in addition to that, in terms of the architecture of how these servers are built, that 100 megahertz reference clock, I caveat this by saying almost always, but so far I've never seen it done the other way. But it's almost always the same clock. So if you have a motherboard with 2 PCIe slots, both slots will get a frequency from a common source on the motherboard. So you can have a common frequency between all of your slots now. So this is why I'm saying that this can be used as a common clock. In PCIe, they call it a common clock architecture. And all the motherboards I've seen have this architecture. So this assumption that I'm proposing, I feel is valid, but I caveat by saying almost always. And so if I have that on the motherboard where I'm getting 100 megahertz from the motherboard now, okay, so what am I doing on the card level? So again, in my architecture, I'm not trying to redesign motherboards or redesign servers. So my most point of flexibility is my PCIe card. And so if I look today at how most PCIe cards are designed, they're designed something like this, where they take that 100 megahertz from the CPU being the motherboard, and they give it to their Ethernet chip. In this case, I'm using an Ethernet NIC as a reference design. They take that 100 megahertz and they give it to their Ethernet chipset. And then they need some other clocks to run Ethernet. So typically Ethernet will run using a clock of like 156 something megahertz. Some chips use different frequencies, but it's not based on the 100 megahertz. And so this means that inside the chipset and even on the board and as in general, you have a 100 megahertz clock and you have some other clocks, and they're not related to each other at all. And so basically you have a asynchronous clocking domains. You have one domain based on the 100 megahertz for your PCIe, and you have some other domains for Ethernet or other parts of your chip. So this is a totally asynchronous design and not taking advantage of the 100 megahertz. And so my proposal for PFM is instead to take that architecture. Again, you typically have a PLL or something on the board to generate whatever frequency your chip needs. Sometimes you just use a direct oscillator, but sometimes you use a PLL. And so replace that with a DPLL, and now give that 100 megahertz you're getting from the CPU to your DPLL. And so now if I have a card like this, that 100 megahertz can be measured by the DPLL in the same way that the common view reference architecture needs. So you have some reference R that you measure at both sides. You need to have some way of measuring that one. So in my case, I'm saying you can measure that with the DPLL. And now you can generate all of your clocks for your chipset based on that reference clock, that common reference. That I'll get into a little bit more detail on that in a second. But basically now you can control all of the clocks for your PCIe card from a common source, from your DPLL. So depending what your use case might be, you can make them all synchronous. You could have them be one synchronous to another or another one from another source. But basically you now have control over it, and you can, in theory, make an entirely synchronous PCIe card because you're controlling all the clocks. And so why am I even proposing this as a architecture? Goes back to my idea of how do I scale this. So looking at a system like this, assume that this block diagram is a single server, let's say, and I have 2 PCIe cards and 2 PCIe slots. And for some reason, I pick one card as the source and the other one as the follower. Not really important for this example, why? But let's say that I want to take a frequency from my card 1 and generate frequencies on my second card from the first card. And so the way this would work is similar to my common view reference example, where card 1 will measure on its DPLL versus the 100 megahertz, its local oscillator, and give that relationship to the second card. And the second card can then generate output frequencies based on the 100 megahertz measurement. And the output frequencies on my second card now will be traceable back to my first card. So there is some software involvement in this. Again, I'm not going into all the details, but basically now I'm taking a frequency from a local oscillator or from some frequency source on one card and generating frequencies on the second card based on that. I'm not tracking the 100 megahertz. So this is a very key point. The 100 megahertz is only for measurement in this case. So even if the 100 megahertz is not a good source, I don't need it to be a good source. I just need it to do the measurement against at both sides and then transfer that data from one side to the other. So back in the common view reference, you have your source and your destination and your reference. You're not trying to track the frequency from the reference. You're only using it to measure and transfer that measurement data between the source and the destination. So with an architecture like this, I could take a frequency from one PCIe card and generate frequencies on another PCIe card based on that other card. And I don't need to do anything. I don't need cabling or I don't need a custom motherboard. I just measure versus the 100 megahertz in my chassis and use that data to transfer the frequency. So that's a key point about this, that I'm not tracking the 100 megahertz. And so that's in one system. So this architecture is how it would look if I have one server, 100 megahertz is going to every card, and I can transfer data back and forth between the cards, and I pick some frequency source, generate elsewhere based on that source. So then talking about the scale out case, so in the case where you have more than one system, I thought it would be helpful to look at kind of how architectures are built today. So the two architectures that I'm comparing against are what I SyncE and White Rabbit. White Rabbit I would consider more of a expanded version of SyncE. But basically, if you just look at how the frequency distribution works, they need a direct connection to whatever device they're trying to send a frequency to. So in the case of SyncE, your clock is recovered from your Ethernet link. So if you have like a RJ45 or a fiber link, you're getting a direct link to your source, same as the one-way transfer. So your Ethernet device will pull out the clock that it's getting from the other side and give that out as maybe a clock output. And then you take that clock output and give it to, say, a DPLL. The DPLL then generates other clocks to other chips based on that. But this is still similar to what I mentioned earlier in terms of a one-way transfer. You have a direct connection to your source to your destination. And the same idea applies to White Rabbit, where they use SyncE plus, they do a lot of really cool stuff, honestly, but they basically still have that architecture of you need a direct connection from your source to your destination. So if I want to get time and frequency through a White Rabbit network, the place that I need that frequency and time needs to be a White Rabbit node. So I need to have a direct connection through a White Rabbit network between my cesium clock in this example here that has GPS and my actual device. There's a path through the network directly to the node that I'm trying to consume time. So again, this is similar to a one-way frequency transfer architecture. And so for what I'm trying to say is we don't need to rely on a one-way frequency transfer mechanism anymore. I can use this method now to transfer it through a single link to multiple devices. So in this example drawing that I'm showing here, I have two servers now. On one server, I have one PCIe card. On the second server, I have, let's say it's the same PCIe card, the same, you buy two of the same kind. And you still use PCIe to get the frequency off the chip. So I don't have a magic for that. But basically you have a PCIe path now. So your local oscillator 1 on your server 1 is your source. The DPLL gives that to your Ethernet chip. The Ethernet chip is sending that frequency over Ethernet, and it's recovered on the other side by PCIe. And that Ethernet chip on the card will give that PCIe clock now to the DPLL on the second server. And so now what you can do is you can take a frequency from one server, give it to another, and inside of the second server, you can measure the PCIe clock that you get out of that link and measure that versus the 100 megahertz in your second server. And so now if I had, let's say, I didn't draw it here because it makes it a little cluttered, but if you had, say, two PCIe cards in your second server, because you're connected to the same 100 megahertz in the second server, you can take your PCIe clock and generate clocks on your other card based on that. So I no longer have a one-way frequency transfer path from my source to my destination, but instead I have one connection path, and then I scale it by using the 100 megahertz common view clock in the destination server. And so the terminology I came up for this was basically a frequency boundary clock. So most of us in the timing industry are familiar with a boundary clock, but the principle is you have a device that takes a source and distributes it to multiple devices. But typically with time, it's through software or some type of software mechanism. And so you have, let's say, one interface getting time from one source, and then it has multiple interfaces. Inside the system, it's taking time from its source, giving it to its destination interfaces, and then sending that out. And so this architecture is the same idea, but for frequency now. So I can now have one connection from my source to my device, and then I can take that one connection and distribute it internally to other devices over this 100 megahertz measurement path. So I no longer have a direct connection. I instead only need one direct connection now. So this is kind of the PFM architecture that I'm proposing. And so that's frequency. So PFM obviously is frequency. So what about time? So again, I'm not inventing anything new here. Kevin gave many excellent talks about PTM, what it does. But for the gist of it is it's PTP over PCIe, and that's how you get precision time over PCIe. So I'm talking about frequency, this is about time. And to do that, you need the system and the endpoints in your cards to support PTM. And so some of the measurements we've done recently with different PCIe devices and PTM-enabled servers show that you can get between two endpoints. So if I have one server with two PCIe cards, I can get a PTM to sync the two cards to within 15 to 30 nanoseconds. So if I measure PPS out of two devices, basically the 1 hertz signal, they will be within 15 to 30 nanoseconds of each other using PTM. And so if I use that, then let's say I have a pulse per second output or input to my device, I now can generate a time over PCIe and give that to my DPLL and use that as my time reference now. No, this is not frequency, this is time. And to do that to the DPLL, I need to give it the pulse per second to establish that time. And so if I have 15 to 30 nanosecond time between two PCIe devices, and now I put PFM on there and I have a stable frequency between the two devices, you can now average that 15 to 30 nanosecond errored signal down to less than 1 nanosecond. So the way to conceptualize this is if you had two wristwatches, let's say, and you could only adjust time, one of them will be faster or slower than the other one. You would continuously have to keep clicking it. Let's say if it was off by 1 second every minute, you would have to go back and click it every minute. Hey, go back 1 second or go forward 1 second, because the frequencies are different. And even if you know the frequencies are different, you only have control over time. So you just continuously have to go back and mess with it. and the resolution that you can change it is only at 1 second. So your error is between 0 and 1 second at all times. So you have a pretty errored times value. But if I gave you control over the frequency, you could say, oh, okay, I see that they're drifting at my source and my destination. They go off by about 1 second every minute. And then you would adjust the frequency on the one you're trying to make follow the source. And you would say, hey, speed up a little bit. And then now the next time around, you'll see, oh, it's only off by, let's say, half a second every minute. And then you say speed up again. And eventually you'll get to a point where the frequencies are pretty close. You no longer have to go back every second and say, okay, go back a second. Instead, now you only have to do that, let's say, every hour. And eventually, as you get a better lock between the two frequencies, your error in time will get lower and lower because you're having to make smaller and smaller adjustments over time. So even though you have a time error between your devices, once you establish a frequency between them, you no longer have to make these large time jumps. You can say, okay, on average, the time error is this, but I know the frequency is the same. Let's take a longer term view of that error, and I can now do that. And the DPLLs have this capability. I'm not trying to show all the capabilities of DPLLs, but in general, they can do this function of averaging down the time error. And again, this is a common thing done with GPS devices where your GPS device is 15 to 30 nanoseconds jitter, and you put a very stable oscillator behind that DPLL, it can now average that GPS error down because you basically have a very stable frequency behind it. So this is not a new concept, but basically I'm saying you can now build this with PCIe devices. And so this diagram is to kind of show the full solution, I would say, where you have PCIe cards in a device with DPLLs that have a PPS connection also from the PCIe device. In this case, I'm drawing it as an Ethernet chipset. And so the input or output doesn't really matter. Basically, you just need some way to get time data into the DPLL. And so if the DPLLs now can measure frequency, and I can take the frequency from, let's say, card 1, generate frequencies on card 2 based on that, that 1 PPS signal that I'm generating over PTM, I can now average down on the DPLL, and I can now generate a time signal between the two cards that's less than 1 nanosecond error with no extra devices. So this is all PCIe card based. And so this architecture here in this picture is kind of the full solution. And so to kind of sum up what I'm proposing, basically with PFM architecture alone, so if you don't have PTM, I could take a commercial server or motherboard, consumer server deployment, anything, from any vendor, because the 100 megahertz is a mandatory clock. And I can now source and distribute frequency to any PCIe card installed from any other PCIe card installed with PFM. And to add on to that, if I had PTM also, I can now take any commercial server that supports PTM from any vendor and install these PCIe cards, and I can source and distribute frequency and time to any PCIe card from any PCIe card in that system. I'm no longer limited by cabling restrictions or Ethernet port restrictions or any other type of custom design that would typically be used to distribute frequency. I can now take a commercial server and turn it into now a frequency distribution and sourcing device. And so to look at some applications, these don't exist today in terms of using PFM, but in my architecture, these are how I imagine this would be deployed. One application would be for 5G ORAN or ORAN type applications using a radio network. To give a little background on ORAN, some people might not know all the details, but basically you have a radio network and you have to get time and frequency through your radio network in order to keep everything running between different towers. So this diagram is from Calmec's presentation about different architectures used in 5G. But basically you have some source, typically GPS, that is going into some device, and it needs to propagate that time and frequency all the way through the network to the radio tower, to the RU is what they call it. And so most of these devices in that path need to operate both in time and frequency. You have to transfer time and frequency from your golden source all the way down. And so this is a picture of one type architecture where you have multiple hops to get to where you ultimately need time and frequency. And the time error that they're looking for is typically less than 10 nanoseconds per device, because you have to go through multiple hops. You can only give so much budget per each hop in terms of how much time error they add. And they also need to have a stable frequency path through the entire system. And so in order to meet this requirement, most ORAN devices today will build everything into the motherboard. So because they need to very tightly control the clocking both into and out of the network, they have to build all of that into their motherboard. So this means they have to build the PCIe to Ethernet chipset plus the GPS or DPLL or OCXO into the motherboard in order to do this stable time recovery, time transfer. So the GPS is optional, but most boards will have a DPLL and an OCXO or TCXO, some type of stable oscillator, together on the motherboard with the Ethernet ports that they need to be time sensitive. And so just as a quick background for people who may not know about the time card is our PCIe architecture for basically separating out the network from the time. So you have your GPS and your atomic clock, let's say, on your one time card, your PCIe card, and it exposes that through SMA and through PCIe. And so this is how we are doing time currently in Meta, is with time cards. And so then the next step would be, okay, you want to make this into a DU or a 5G type application, you have to consider frequency. So I could respin the time card. In fact, I don't have the CAD on here, but I could put a DPLL on the time card now and install that into my server and now make a 5G device. So for this example, my time card is my frequency source. So it would be locked to GPS. I have a GPS receiver. It has an atomic clock or some type of high stability oscillator on it. And that's it. And then PCIe and the DPLL. And then my Ethernet NIC that I need to actually use the time on, I can now use PFM plus PTM to get the frequency and time from my time card onto my NIC. And now my NIC frequency is traceable back to my GPS disciplined oscillator. So this means that my PCIe NIC now is just following my time card. I don't need a GPS or anything on my NIC anymore. Everything is on my time card, and I'm just giving that to my other devices in my system, in this case, my NIC. So now all the clocks on my NIC, including the Ethernet clock that goes out over SyncE, is backed by my GPS disciplined atomic clock on my time card. So effectively, I built a time and frequency grandmaster using just PCIe cards. I didn't build anything into the motherboard, and I didn't build a custom server. I just plugged in cards, and now I have time and frequency backed by GPS and an atomic clock that goes out over an Ethernet network. And so just to reiterate that point, if I have PTM and I have PFM, I can take any server from any vendor and source and distribute frequency and time to any PCIe card installed. So if I need a 100 gig interface that's time and frequency backed by GPS, I can do that now with PTM and PFM and create 5G compliant devices. So I can take any server and make a 5G compatible grandmaster. Or if you don't want it to be GPS backed, again, back to my previous slides, you just put multiple cards and the software will pick one card and give that frequency to all the other cards over software now. And I can still make 5G compliant devices with just commercial servers at any scale using any type of ports that I want, because it's all on PCIe cards. The second application that I'm highlighting today relates to distributed AI. So this is more to show that I'm not limited necessarily to Ethernet applications. And so for a typical distributed AI application, you will have some Ethernet device in your system, But your GPU or your accelerator cards are usually just PCIe devices. They don't typically have a direct network interface on them. But this architecture for PFM can apply still to AI because I'm still just inside the system on the PCIe bus. So even without PTM, I can sync all my GPUs or accelerators in frequency because I can just generate a frequency on my GPU card based on a frequency on my Ethernet card. So now if I had, let's say, 10 GPU cards in my system and one Ethernet card that connects up to some better frequency source, I can now generate frequencies on my GPU cards that are all synchronous between all my cards and also synchronous to another source. So I can now just create a frequency aligned GPU cluster. And if, let's say, in the future, GPUs or accelerators have PTM with PPS, I can now do what I mentioned earlier with time and frequency now. I could now generate and create a distributed AI cluster with a common time and frequency across all of my accelerator cards. And I could distribute that or source it from any connection in my system. And so what could I do with this? Basically, like I said, if I only have PFM, I can take any server from any vendor and make a frequency synchronized AI cluster. So every GPU in my cluster will run at the same frequency. If I have PTM also, I can now create a time and frequency synchronized AI cluster, distributed AI cluster, using normal servers from any vendor, as long as my cards support PTM plus PFM. So applications for this include where you want to distribute load across your AI cluster. Let's say you have a backend network that, this gets into a little bit of the detail of AI, but you have an AI backend network where all the GPUs need to talk to each other between systems, and you want to very accurately schedule when things will go from one card to another because you're going over a network now, and you don't want to overload your network. If you have a very accurate frequency and time synchronization across your entire cluster, you can now very precisely schedule data communication between devices in your cluster. You can now precisely schedule when certain trainings happen, when they stop, who did what when. So for example, if one device made an error in its calculation for some reason, you can now exactly know when that happened between all your devices to, again, like sub-nanosecond level accuracy because you have a common frequency and time everywhere. And so I'm a hardware guy. People who know me, I like to spin boards. So this is the initial prototype that I built. Actually, since I made these slides, I've spun 3 other boards with PFM architecture. So I didn't include them in these slides, but they're on the GitHub right now, including a time card V10, which has PFM. Again, I don't have in my hands, but they're in process. And so my initial prototype is a card like this. So this card implements all the features that I'm talking about. It has a DPLL from Renaissance that connects to SMAs, which I can use for measurement purposes. It has 3 ports of 1 gig SFP that have SyncE PHYs, so I can recover the clock from the Ethernet connection and give that to my DPLL. And then the clocks that I'm giving to those Ethernet chips is from my DPLL. So they're all synchronous to the same source. I'm giving 100 megahertz from the PCIe directly to my DPLL. And then I'm also giving those frequencies to my PCIe chip. In this case, I'm using a TI microprocessor, which has PCIe plus PTM. And so with this I also have a M.2 GNSS, which is a recent OCP contribution in terms of the pinout, but I put everything on there to make a complete solution. And so with a card like this, I can fully demo the PFM architecture with PTM, where I can now use PCIe to transfer time and frequency, and then also get that out over Ethernet and measure it on SMA inputs or outputs. And so with this, I will be able to show basically the entire stack. From inside of one system, I can transfer between 2 cards with the DPLL and PTM. And then outside of the system, I can transfer it using SyncE plus PTP. and then I can measure it with the SMAs. And I can even make a grandmaster with GPS if I'm so inclined. And that's my initial prototype. Again, I have a couple others in the spin. And that's the whole slide deck so far. So there's a lot to this. I'm sure there'll be questions, but that's what I have so far. So that's all I have.
Wonderful. Thank you very much, Julian. So let's open the floor for questions. Eric.
Sorry, I'm pretty new to this. I'd like to know, are people using the PCIe's PTM very much nowadays, or only a very specialized application will use PTM on the PCIe?
Ahmad, do you want to tackle that, or you want me to?
Take the first kick.
Okay. Actually, this is something I'm still learning about. Even today, I learned that PTM actually is used extensively for industrial applications, where you have distributed I/O that you need time synced. So you distribute time over some Ethernet or cabled network, and then you have some kind of endpoint that you need to have basically like time triggered outputs. But your device is connected from some Ethernet or something like that to a device that has a PCIe connection to where the I/O is coming out. So you need to use PTM to get that accurate time down from your network to some other device. So I didn't know that, actually. That's new to me today, actually. But for the PTM in the other side of things, what I would consider my normal background in servers, it's kind of early right now. The PTM capability came out with Intel Sapphire Rapids, and there are some devices. We maintain a list on the OCP wiki about the devices that we know about that support PTM currently. Most of them are Intel CPUs and then some Ethernet NICs, along with the TI microprocessors I mentioned, and some FPGAs. So that's kind of the domain that I know about for PTM today. And it's not that there's usually a limit, it's just usually people have to think about that when they're designing their PCIe endpoints. Ahmad, if you want to take a more stab on that.
So basically, Eric, PTM is a good way to get precise time to the user land, and basically synchronize the timestamp counter (TSC) of the CPU. And with that, there are two types of things you can do in terms of classification. You can either measure things precisely now in nanoseconds, I mean single-digit nanosecond, or you can trigger things also in nanosecond. Like for example, you can either use RDTSC is an assembly instruction to take a snapshot from the TSC that is synchronized, let's say, by a PTM, and it's not synchronized. I mean, there's a lot. Like you get basically two corrections. It's like a slope correction, the linear correction, which you have a slope and an offset, and then you take the TSC, but then you get also the slopes and the offsets for that current time, and then you apply them. Or you can use something called a T-pause, which is a pause that uses a TSC in terms of precision to basically put the system on a no operation until you basically finish that time. And I'm not aware of an interrupt vector, but there is a hardware vector which is called PCIe that can issue a toggle on a pin. So if you have, let's say, every 500 millisecond one of these, you can have a 1 hertz pulse coming out. I hope this answers your question, Eric.
Oh yeah, thank you. I think the other question is for any PCIe or NIC card that support PTM, it has to meet the I'm sorry. So the PTM is defined in an PCIe 4.0 or 3.0 or above. Like starting from which PCIe version that PTM?
I think 3, but it's optional, right? So like they define how the TLPs, the custom packets that they use over PCIe to implement PTM, I think is defined in 3, but I could be wrong.
Yeah, PCIe 3 added PTM,
I
Right.
see.
but it
Yeah.
was
So,
not implemented up to
if I
recent
buy a PCIe card from a vendor, if the vendor claim that it's up to the PCIe 3.0 standard or 4.0 standard, I would expect that this card will support PTM. Am I
No.
correct? No.
No,
No,
it's an optional feature. Go, Maciej, go.
yeah, I just wanted to say the same. So it's an optional feature, so only the cards that's actually implemented the whole PTM logic will support that. And there's not many of them.
Yeah. But we're trying to think.
So even a NIC PCIe 5.0 card, it's
Yeah.
still optional to support PTM. Am I
You can
correct?
have a 5.0 and no PTM. And really, we want to change that.
I'm sorry, 5.1 without PTM? Is that what you're saying?
You can have a PCIe 5.0 and have no PTM on it. And
I see.
so many devices that they don't have it. But we really want to change this. Again, how do you change it is when you have more support and more demand for it and
Right.
applications, right? So, and we hope like with PFM, we can also take like the gap that is there that like, no, we just need the frequency, or like we need the frequency as well. Well, here's the frequency.
Got it. Thank you. Thank you. Yep.
So I think Dan asked a question, Julian.
I was typing a reply. Yeah. So Dan's question, if this is on YouTube, was how long were your measurements to get nanosecond accuracy? Were they over minutes, hours, days? Was this a 99.9999% value? So I was typing an answer, but I'll just say it. So basically, this is all architectural proposal, right? So even I don't have the first cards with this architecture in my hand. I'm spinning them now, and I will get them probably later this month. But even those, I still have to power on and bring up and stuff. And I didn't really want to delve into the devil in the details too much in the presentation to scare people off. But it's a very tightly coupled system, right? There's software interaction, software filtering, your DPLL accuracy, your local oscillators on both sides, things like that when you take your measurements on your DPLL. And so I don't have any numbers at the moment for values. That's why I'm building the prototypes, like I said, to have somewhere to prototype this. If someone's interested in working with me on those prototypes, I would love to have help, but otherwise I'll keep chugging on our own internally. But the measurements in terms of like what we're expecting are currently, I won't promise numbers. I'm just saying that in general, typically when you talk to a DPLL vendor, they use the DPLL for that purpose, where you have a GPS signal, let's say, with 15 to 30 nanosecond error, and then you have some high stability oscillator like a OCXO, TCXO, and they do that averaging down in time error. And then the output from the DPLL will be a much better time signal. So that function is more what I'm trying to emulate. Not, the exact numbers, again, there's a lot of factors in this system. It's a kind of there's a lot of moving parts. So I don't really have numbers, and I don't really have simulations at this point. It's more of an architectural idea for how to solve these problems. Steve asked, have I talked to any 5G DU providers to discuss this concept yet? I have not. I would love to talk to anybody who's interested in implementing an architecture like this, or asking others to implement an architecture like this for them. Me, myself, like Ahmad said, I'm a hardware engineer at Meta, so I have a day job more or less. And I build these prototypes for timing applications on my time also. But in terms of, I'm not someone who works regularly with 5G providers or 5G DU manufacturers, let's say. Yeah. And actually the product chain that we would need to discuss this with might get complex, because the server manufacturers are probably the ones getting specs from, let's say, the providers. And so the providers would have to say, okay, I want this architecture instead. So I mean, if anybody wants to set up a meeting with us and people who are interested in an architecture like this, I'm more than happy to talk about it with anybody, really. I just haven't gone I don't really have the connections for that at the moment, and I'm not sure the right people to talk to, but I'm more than open to anything. So, yeah, that question, okay, so this is the getting into the devil in the detail question. So, so this is from, I don't want to say your name. Okay. So the question is, it seems to me that the stability of the 100 megahertz PCIe clock might be a limiting factor. Since I understand correctly, this is frequency used as a common reference. So this is actually something that I've heard quite a few times, and this is true because you're measuring versus this frequency. If your measurement is versus an unstable frequency, depending on your time of measurement, you will get a kind of a built-in error. This is something I've discussed actually quite a bit with quite a few people I've talked with this about. And this is something that I've talked about with the DPLL architects at Renaissance about, and I had a proposal for how to solve this or kind of solve it. And again, this is very early, not implemented anywhere, but my proposal is if you have PTM, you now have a common timescale between DPLLs on different sides. Inside the DPLL, you could set up a triggered measurement. So you would say like at time 10 on both devices, measure versus the 100 megahertz.
Yeah.
And so now you're not, it's like PTP where you're doing hardware timestamping. Here I'm doing hardware timestamping of the frequency measurement. So even if my 100 megahertz is drifting or, you know, particularly has bad long-term characteristics or even short-term, as long as I instantaneously measure that at both sides at approximately the same time, you should be able to do that measurement comparison. So that's
differential, because it's a differential measurement. So
right. You're comparing the difference in measurements at both sides versus a common source. If you do that measurement at different times versus a poor source, that differential will not be very accurate. But you can generate now with PTM a common timescale to do that measurement also, and you should be able to limit that source of instability in the measurement. Again, this is all theoretical, so I want to caution.
This method is basically using the same 100 megahertz that is distributed across all the devices for precision, not for accuracy. And then when you, I mean, as long as 100 megahertz exists, is within a ballpark, it should do the job. So because you're also triggering it at the same time. But I mean, I'm waiting, as Julian mentioned, like for the hardware to come. Then we do some lab tests, and then we carve out the math, and we see like how we can analyze this better.
One other point.
Yes, I think if you can trigger the measurement at the same time, it should remove most of that error.
Right.
It should help a lot.
That's my initial proposal for solving that. The other proposal I had was if I don't limit myself to existing motherboards, if let's say there's a customer, like let's say in finance, who, you know, they have the money to build what they need, I can now just tell them, back your CPU clock with the OCXO, and basically now your entire system can be super stable, frequency synchronized. Then I mean, that's the other option. For me personally, I was trying to avoid any kind of like server change. Yeah. But if your real interest is in very stable frequency transfer, like much better than I can do with the kind of like low accuracy, high PPM, 100 megahertz that exists today, the next option would be, again, back to the 5G space where they build everything into the motherboard. I don't need everything built into the motherboard. I just need the source of that 100 megahertz to be stable. So you would just ask your motherboard supplier, whoever, to say, okay, don't put just some crystal, put some TCXO or OCXO behind your 100 megahertz clock, and then that solves that problem. So there's different ways to solve it. The time triggered way I feel is a little more elegant because it kind of follows the hardware timestamping idea of like PTP. But if you're really interested in very high performance, you have to start considering things like that, the 100 megahertz as an error source. This question from Nobu in the chat. So when you combine PFM and PTM, I had the impression that clock comparison is done with PPS, but you can compare at much higher rate than 1 sampling per second. Is that correct? So for the frequency measurement, you're basically limited to your serial bus, whatever you have to the DPLL, because the amount of data that you have to transfer from one card to another in a PCIe architecture is very small. So PCIe is, 8 gig or something or more. And we're just talking about small bits of serial data. That's relatively small amounts of data for a PCIe device. But if you want to sample, let's say, if I want to have both my cards sample versus 100 megahertz at, say, 20 times per second, you can do that. You just need to be very good about, like I said, the time triggered of when your measurement is, and then also like the reading from the DPLL. So most DPLLs have a I2C or a SPI interface. So your Ethernet device will need that serial connection to the DPLL, and then your software will have to take the data from one card, give it to another, and you would want to do that 20 times per second. So the time comparison would only be at 1 sample per second, because you're still relying on 1 PPS in general, but your frequency comparisons could run pretty much as fast as you can do them, as you can get the data out of one card and put it in another card's DPLL. That's pretty much the only limitation that I see at this point. That's, again, I don't have numbers for that, but there would be some serial communication bus throughput limitation on maximum frequency transfer update rate, depending how you connect to the DPLL.
Okay, thanks. So, I mean, so my question is more like, so we have 1 PPS cabling, and are we really limited to 1 pulse per second, or can we do like 100 pulse per second and do the comparison? I'm sort of asking physical sort of limitation.
DPLLs can go nuts, right? They can measure pretty much anything. At some point, if you have too many time samples per second, you'll run into the same serial bus throughput limitation. If you need to read out timestamps at 100 timestamps per second, and each timestamp is 80 bits, that will start to saturate your connection. And then the other problem would be is which edge is what exact time. That's additional data you would have to give. But there's no limitation from the DPLL side in terms of it has to be 1 hertz. They can all take, the higher end DPLLs can all take 1 hertz to whatever, 700 megahertz, and you can give it timestamps for the edges. It would just be more like a logistics problem at that point.
Yeah, bottleneck would be the data transfer rate to catch up.
And you also don't want to saturate that data because you still need to do the frequency measurement transfer stuff too. So you need to like kind of bandwidth limit yourself so you don't saturate that. So, and the 1 PPS is a common frequency, right? When we debug Ethernet NICs in our lab, they have 1 PPS, but they don't usually have like a arbitrary frequency generator. But if you do have a kind of arbitrary frequency time generator, then there's no reason you couldn't do it for like 2 PPS or something like that.
Thank you.
Sure.
Any more questions? Hearing none, we're on top of the hour, and we'll see you guys next week with, I think, yeah, it's next week. Yeah, we have next week another call, and wish you a great rest of the day.
Yeah. Thank you, everyone.
Thank you.
Thank you. Bye-bye.
Bye.
Thanks, bye.